Hello and welcome to another video. In this video we're going to be doing frog jump. And so in this problem it's pretty straightforward. A frog is crossing a river and it's divided into some number of units, and essentially you have this stones array where at all of these indices a stone exists, and the frog starts at 0 and needs to get to the very end, and its first jump has to be 1, and then subsequent jumps have to be either k or k minus 1 or k plus 1 units. And also these stones are in ascending order. So for example, in this first one, if you start at 0, we can even make it bigger if we want to. Let's do that. There we go. Okay, so if we start at 0, we can jump 1 stone here, and then we can jump 2 stones, and then we can jump 3 stones. Actually, no, sorry. We'd want to jump 1, 2, 2, 3, 4, 5, and then we get to the end. So our jumps have to be increasing or decreasing or the same, but they can only be increasing or decreasing by 1 unit. So if we try that here, we can't really get past this little gap here, because if you see, like, we can jump we have to jump 1 unit here, and then no matter what we do, we can never do anything, right? So we can jump 2 units and then 1, and then this is 4. So in order for this to succeed, the jump to this stone has to be 3 units, and you can't really do that, right? From 1, you can't get to 4 with 3, because you can only jump 2 or 1 in either way. It doesn't. So we need to basically rearrange this to make this a little bit more useful, because, like, let's say we're at this stone and we just jump like 10 units or something, and we're like, all right, we're at stone 11. Well, where is stone 11 in the array even? Like, do we want to just like manually go through the array? That doesn't seem like a great idea. We want to just be able to say, is this stone in our stuff or is it not, right? And so the easiest way to do that is just convert these stones into a set. So we're going to convert this into a set, and we are going to store the first and last value just to know, like, where do we start and when do we end. So our first here is going to be 0, and our last is going to be 17. And then it's pretty straightforward. It's actually, like, I'm surprised it's a hard problem. You only have a few things that you could do at every step, right? You can only jump 1, or you can only jump k or k minus 1 or k plus 1 units. So what does that sound like to you? Well, it sounds like a dynamic programming solution with not too many choices. You can only jump, like I said, you only have 3 choices. And so for a dynamic programming solution, what would we have to do? So for dynamic programming, we have 3 things, right? So we have state, then we have a base case, and then we have a recursive case. And what would we use for these, right? Like, what would you use for the state? Let's just think about that first of all. Like, what do we need? Well, we probably want to know what stone we're on, right? Like, that one's pretty straightforward. We have to know, like, the number of the stone. But what else? Do we need anything else? Like, how do we make our decisions? Well, if we jump k or k minus 1 or k plus 1, what is k, right? Like, we have to know how far we can jump, and so we have to store this, like, k or jump variable. So we'll just call that k. Okay. And then from there, we just know we can jump either k minus 1 or k or k plus 1. And so what's our base case? Also pretty straightforward. There's a couple. So A, let's say we try to jump on a stone that doesn't exist. So stone not in stones set. What should we do there? Well, that basically means we landed in the water. So we'd want to return false. Okay, well, what else do we have? So we can also make it to our final stone, right? So stone equals final stone. Like our stone we need to get to. What should we return there? We should return true. And then what else do we have? So we have a cache. But remember, I think I've done a lot of these problems where you're just trying to return one solution that succeeds. And so anytime you're trying to return one solution that succeeds, instead of doing a cache, you can also have a visited set instead of a cache, because everything in visited is always going to be false, because if you ever get anything that is success, then you can just immediately recurse out and return true to the whole thing. Like, we're not asked how many different ways can the frog get to the end or something, or what are all the arrays of the ways. It's literally, can it get there or can it not? So our last thing is going to be, is stone in visited set? And then if yes, return false. If not, we just keep going, because everything in the visited set will be false. Okay, well, what about for our recursive case? Like, what can we do? Well, this one's pretty straightforward. We jump k or k minus 1 for k plus 1 units, right? And we just update our state of dp accordingly. Like our stone will be stone plus k, or stone plus k minus 1, or stone whatever. And then our jump will also be like let's say our previous jump was 5 units, and now we jump 6 units. Well, we want to pass 6 into the next state, because then we know we can jump 6 or 6 minus 1 or 6 plus 1 units. So that's all the recursive case is. We just try all the 3 jumps. But there is one more thing we're missing in this recursive case, so hopefully you've been able to spot that. So we don't want to jump 0 units, right? Like if we jump 0 units, we can just get in an infinite loop where we're jumping 0 units over and over and over and over. And so what we need to do is we need to check for that, where our jump, we do want to jump k or k minus 1 or k plus 1, but we never want to jump 0 units. So we will check for that to make sure we don't have that happen. And that's pretty much it. There is one other optimization you can make, and I will show you that. And it'll be pretty obvious once I show you this example. So let's say our stones are 0, 1, 2, 3, 4, 100. And I say, is it possible to get to the end? Well, it's pretty straightforward that you can't, because at each jump, you can only jump one more time, right? So here, so how many jumps do you have? We have jump here, jump here, jump here, jump here, jump here. You have 5 jumps, and what's the maximum you could possibly jump? So here you jump 1, 2, 3, 4, 5. Well, obviously this is not going to get you from 0 to 100. So because our numbers, because we know how far we can jump, right? Like the most we can get to is 1 plus 2 plus 3 plus 4 plus 5. So what would that be? That would be 9, 12, 14, 15. And so the biggest number we can possibly get to would be 15, right? Like, because we'd be at 1, then we'd be at 3, then we'd be at 6. Oh, did I do that right? Let me see, actually. So we have 1, 2, how many jumps do we have? We have 6 numbers. Yeah, so we have 5 jumps. And let me just double check that one more time. 12. Yeah, I think we should be able to. Let me just double check that. So 1, then we'd be at 3, then we'd be at 6, then we'd be at 10, then we'd be at 15. Yeah. So if this was 15, we could do it. But these also have to be obviously these have to be bigger. That would be doable, but this is the biggest number we can get to given this length. So is there a way to calculate quickly a sum of an arithmetic series that increases by 1 digit at a time? So let's say this is n digits. And so there is a way to do that. And it's literally the sum of a n-1 length sequence is n times n-1 over 2. And let's try that in this case. So n here would actually be 6. So this is n-1 length. So it would be 6 times 5 over 2, which would be 15. And so we can just check for that in the beginning. We can just say okay, what's the maximum we can jump? Let's calculate that. And if the maximum we can jump is less than this number, then obviously we don't need to do our whole DP. We can just say false. So that is a slight optimization, because you can do that in big O of 1 time, right? You can get the length and you can get the last number, so that's pretty nice. So we are going to include that in, and that's kind of maybe if it would still pass if you didn't have it, but that's just something you could add. So we are going to include that. But other than that, it's pretty straightforward. So let's start coding it up here. So remember, first we're going to check for that optimization, where we're going to say, if we can't get to the end, because it's if we just take the biggest jump at every single step and it's still too small, we can just return false. So that's going to be if stones -1, the last stone, is greater than. And so remember, you have to take the length of the stones. So length of the stones times. And so if the stone is length stones, then our n jumps in that example would be actually n-1. So remember, this is the formula to get the sum of n-1 stones, and n-1 is the number of jumps. So that would work in our case. So if it's n-1 is the number of jumps, then this would be n, and then n-1 would be length stones -1. Okay. And then we need to actually put that in parentheses. And we need to also divide it by 2. And this should always be a positive number, because it's essentially an odd times an even number, which is always, it should always be an even number. So this floor divided by 2 is fine, because it'll always be a full digit. Okay, so we can just return false if that's the case. And now what we're going to do is we're going to have our visited set. So we're just going to visited set. And then we also need to want to record the first and last stone. So let's do that as well. So we can say like first stone, because just so we know where we're starting at, equals stones 0 and stones -1. Okay. And now we're literally going to transform stones into a set. And if you think you don't want to be manipulating stones, you can make a new set. So you can do that as well. But I'm just going to do it in place. So we're just going to say stones equals set stones, but you could make another variable if you wanted to. Totally fine if you don't want to manipulate your inputs. Okay. So now we have our DP function, and remember it's going to take a stone and a k, right? We said. So I think I used jump before, but we can use k. So what's our base case? Well, if stone equals last stone, then we want to return true. Okay. And what's our false cases? So if stone not in stones, meaning it's water, or stone k in visited, meaning we already went there, it's everything in visited is false, we can return false. And now we have the cases for the jumps, right? And so first we can handle the jump that's k-1, so we could say like if k is greater than 1, and remember, we don't want to jump 0 times, so we're just going to say if k is greater than 1, do this. Otherwise, let's skip this step because we don't want to jump 1 minus 1 times. So where's our jump going to be? Well, this is pretty straightforward. It's going to be stone plus k minus 1. That's where it's going to end up. And then our new jump length is going to be k minus 1. Okay, so we can return true here. And then we have 2 more cases. So if dp stone plus k, you can probably clean it up a bit, but it's only 3 cases, so return true. And they all do have like slight differences, so. Okay, and so for our last case, we need to make sure that we basically need to make sure that our stone isn't the, like, if you think about it, this first stone has to be one length jump. And this works for, like, this will be fine for this because k would be 1, so this would never go here. So this would be this. But now we have to make sure in our last case that the first, like the stone we're on isn't the first stone, because from the first stone you can only jump 1. So you don't want to jump 1 plus anything, you don't want to jump 1 minus anything. This is already excluded because of this, and so now we need to check for the plus case. So we just need to say if stone does not equal the first stone, because from the first stone you're only allowed to jump k length, and dp stone plus jump plus 1, jump plus 1. Then what do we want to do? We want to return true as well. And then finally, if we went through all of these cases, then we know we can't succeed from this state. So we just add this state into our visited set. So we want to add, this should be k, by the way, not jump. Okay, so we want to add it to visited, and then we just want to return false. And then finally, we want to call our DP function, and what's our initial state? So our initial state is first stone. And then what's our jump length from the very beginning? It's 1, right? So it says the first jump has to be 1 unit. So that's what we're going to put in. And we are just going to return that. And let's see if we have any errors or anything. Okay. Yeah. So you can see it's pretty efficient. So let's do the time and space complexity now for this. So essentially, if you go back for the time, we are pretty much, like, let's see what's happening. So this is O of 1, and we are going through stones, and you might think that, like, well, every stone can be 2 to the 31, so shouldn't this be like 2 to the 31? Well, no, because the biggest the stone can, like, if the stone is too big, this will just fail right away. So the biggest a stone can be is the biggest jump you can make. So actually, it's still like O of n. And so that's why for the actual number for stone, it's actually the length of the stone's array, not the like biggest value of stone. Because let's say we had some array like I said, that 1, 2, you know, whatever. This is like 2 to the 31. This would just break immediately because this would be false. And if there was ever a 2 to the 31 in here, because it's increasing, the biggest number would have to be like really big. And because the array is only 2,000 elements, it would just break in O of 1 time, because this would always be false. So this check ensures that our time is of length of stones, and our biggest stone doesn't matter. So this is going to be like stones, length of stones. And then the jump also, if you think about it, can go like 1, 2, 3, 4, 5, 6, 7. So the biggest jump is like roughly the length of stones. So all the states for jump would be length of stones as well. So it's stones times stones for time. And then for space, if you think about it, our visited set is going to have this stone and this k. And like I said, for stone, it's still going to be the length of stones, and k is also going to be the length of stones. So they're both the length of stones times the length of stones, which is like stones squared, time, and space. But yeah, I think that's going to be it for this problem. So hopefully you liked it. Like I said, not too hard of a problem. Definitely one of the easier hard problems. And I think in the last week or something, there were like some very hard problems that I said, but I think this one's pretty doable. So if you didn't get it, just try, like after watching this, try to redo it. It shouldn't be too bad. And if you like the video, please like the video and subscribe to the channel. It really helps grow it. So I'll see you in the next one. Thanks for watching.